What is it? Excuse me?
No, the recording. So
Ah.
it's obviously okay by you, I think. Otherwise it will not be here.
I shouldn't make mistakes, otherwise they'll be recorded.
That's always a problem with that. No, you just show that you are human.
There's always Photoshop.
What is that?
Photoshop, yeah. We can Photoshop.
What is that?
It's all the mistakes in, you know.
It makes the speaker more attractive.
Yeah, so if you feel that we need a break of 5-10 minutes in the middle, please let me know at whatever time. So I mean, there is no hurry. I mean, we don't have to fix anyway. We are not going to get into the heart of the thing even at the end, so it doesn't really matter.
Yeah, let me mention to everybody that if there is more interest.
No, we'll have the informal.
Next week. So Ketan is here for 3 weeks, and maybe next week we'll have some, continuation, more informal than this.
No, more informal, not very formal,
Yeah.
no. So that it's open-ended. Yeah. Okay, so let's recall what we have done so far. So So these are the various class varieties, and these are the coordinate rings, homogeneous coordinate rings of those varieties. And yeah, so this is the notation from the last time, and the main decision problems that we were interested in were given lambda, m and d, does the while module v lambda g occur in RV gm star d, given lambda in m and d, does this occur in RV if in m and d star, and then given pi n and d, does d pi h occur in
How is D picked?
Hmm?
How would you pick D?
no, that D actually determine.
I understand, but just in eventually you need to pick D.
No, so the D would be approximately polynomial in N.
Okay.
Yeah. And then the relaxed forms of this, which says given lambda n m d, does vk lambda g occur in RV gm star kd for some k greater than or equal to 1, and similarly relaxed forms of B and C, etc. Okay. So, these are the main decision problems of interest in the search for obstructions. Yeah. And one remark is that we can actually, in all the considerations, we can let G be SLY instead of GLY, and H be SLX instead of GLX, because the point is that these differ only by constant multiple, and the SL orbit of G is the same thing as GL orbit of G in the projective space. Okay. So, everything can be done instead. So, for today's talk actually we will let G be SL and H be SL, and obstructions etc. everything defined in SL, because for the next theorem we will need that. Okay. And and given V, a point in the projective space V, we will let V hat denote any non-zero.
You recover the representation of the full F m knowing the degree of the form. You know on the form on degree,
Yeah.
you know of
Right.
scalar matrices times.
Let V hat denote any non-zero point on the line in V corresponding to V hat. Okay. So, basically if this is V, so through the origin take the line corresponding to V in the space P and take V hat be any non-zero point on that. Okay. So, for example, whenever we say think of determinant as a point in V instead of PV, okay, instead of PV we will denote it by G hat, otherwise there is a confusion, like there was confusion last time. Okay. So, that there is no confusion of that kind. Yeah. And similarly H hat is equal to permanent X, because this distinction is important, otherwise yeah. Okay. And this distinction is important because as we yeah, as we saw yesterday. Okay. And let G of G hat be the stabilizer of this affine version of determinant, and similarly H of H hat is the stabilizer of the affine version of permanent. Okay. Yeah. G is now henceforth SL. Yeah. And for the next theorem actually the SL is going to be important, because we are going to be using stability things, and then GL doesn't yeah, for that. So, we are preparing for that. Yeah. Okay. So, theorem 1 GCT2. So, in the context of those, so what says is that V lambda of G occurs as a sub-representation in RV G star, and by this we mean RV G D star for some D, if and only if V lambda G contains G hat invariant. By G hat invariant we mean of that group, the trivial representation of that group, trivial representation.
When you say for some D, D is fixed.
Huh?
When you say for some D,
No, not fixed. In some D. Okay, so it's not going to tell you in which degree D component, because the point is this is the SL representation. So if it corresponds to something, in principle, you know, you can add any number of these columns here, and it's not going to tell you which D it is going to occurring. So it is less than, yeah, so that is.
And how do you identify the partition for different D?
No. So this only is going to say that it occurs in some D, but it's not going to tell you which D, okay? For some D. So
D is the degree? Or what
yeah, so this is actually so the point is that this is a more relaxed form of this than this, okay? So the other decision problem here would be, okay, so which is the other third problem given
This index D means degree of the form.
of the
No, the degree in the
of in the homogeneous coordinate ring. Yeah, but this result doesn't tell you in which degree thing it is going to occur, okay? I mean, and that is an important point, because so that is a leak. So we would need stronger thing later on, but that is an so the trivial representation, or that others say fixed point, okay? So if and only if this V lambda G contains a point that is fixed by G hat, yeah. So this, and similarly V pi of H occurs in R W H star if and only if V pi H contains H hat invariant.
Can you explain what intuitively it means that it contains this invariant?
So invariant, so the point is
We have a particular
representation of G, okay? So you can, by restriction, you can think of it as a representation of this also, correct? Because this is a subgroup, right? So this is a subgroup of G, so you can think of it. Then as a representation, the thing is that this, okay, so let me say, I have to make one definition which I have not defined. So we'll say that definition, a group D is called reductive if every finite dimensional representation of D is completely reducible. What that means is that it can be written as a direct sum of irreducibles. So in this case, it means that if you are given some representation V of D, it can be written as a direct sum like that, where these are all irreducible and these are all the multiplicities of those VI's, yeah. And so for example, the example is that all the finite groups are this is a classical thing, and the more non-trivial thing is that GLNC and SLNC are reductive, and this is while, and this we have been implicitly using so far. So similarly, all these things are reductive groups, this G hat, H hat, okay. So when you take this V lambda G as this representation, it is going to break into those bricks of G hat. So if there is a brick which is corresponds to the trivial representation in that complex thing, that means it contains a fixed point, okay. Yeah. So that is what it means. So as when contained as this stabilizer, this representation, okay, it contains a trivial representation, the fixed points.
So you view it as the representation of G hat.
Yes, to get a trivial
yeah, so it's some representation of that particular group, and you just decompose it and see whether
the trivial representation occurs in it, yeah. Yeah, and similarly for the other thing, yeah. So in a way, what this thing does is that this theorem reduces the algebraic geometry of class varieties, okay. So algebraic geometry of class varieties, the questions regarding the algebraic geometry of these class varieties, to the representation theory of the associated group couples. Okay, associated, so group couples. So what do we mean by group couple? So for example, for with delta Vg, we associated a group triple yesterday, which is G hat inside G inside K, correct? Yeah. So it is a represent. So this is called the couple associated. This is the triple, and this is the first couple, and this is the second couple, right? So the G module structure of this, we said yesterday that we want to reduce all that study to somehow the representation theory of this. So this is the first step in that direction. Okay, that it tells you what is the G module structure of this in terms of just the representation theory of this couple. Yeah. So okay.
And the second couple will tell you what these.
No, second couple would be required later. Right now the first couple, and then we'll come to the yeah. Okay, so now about the reductive groups, the following thing says, if V lambda from the reductivity of this G hat, one can say that and G, that this occurs by belongs to, we mean occurs, that this belongs to GMD if and only if we take the dual of this V lambda G dual, then that is also an irreducible partition, and that would correspond to some partition, that the dual of this would correspond to some partition. So if and only if this dual belongs to RV, so this all follows from the reductivity, this, and similarly V lambda G contains G hat invariant if and only if V gamma G contains G hat invariant. Okay. So using these properties, actually this statement is equivalent to the same statement when you actually get rid of this star. Okay. Yeah. That it is also true that V lambda G occurs in this.
With another lambda, with the dual lambda.
No. I mean, if you just get rid of this, that statement is also true, because there is this involution. G is equal to SL now. Okay, so there is that involution. Using that involution, so the same statement is also equivalent to the same theorem when you just get rid of stars there. Okay.
So, for theorem 1, are you using the uniqueness of the stabilizer?
No, not uniqueness, but we are going to use that stabilizer is fairly non-trivial, not a complete thing. Yeah, the exact stabilizer would be used, but not the fact that it is characterizing it completely, but that it is fairly big is going to be used. Okay, so the representation theory is going to be used. Otherwise, there is not much. Yeah. Okay, so let's get into the proof of this now, of this theorem. So the proof of 1 and the 2 is going to be similar. So we are just going to worry about the proof of 1. Okay. So first let's take the trivial part. So suppose S equal to V lambda G belongs to RVGM. Okay. And let us denote by this Gm in V, this is the affine cone of delta VGM. Okay. So this is a projective variety in PV. So corresponding to every point there is a line. So take the union of all those lines. So that is the affine cone in V corresponding to this the projective space in this. Okay. So this now one can also think of this as the so this is a homogeneous coordinate ring of this. It's a coordinate ring of this. Yeah. So coordinate ring of this affine variety. Okay. Now suppose that this suppose this belongs to this. Okay. So what we want to then show is that V lambda g contains, assuming this, g hat invariant. This is what we want to show. Okay. Yeah. So the claim is that not all functions in S can vanish at g hat. So the point is, let's look at this g hat and let's look at this orbit of g hat. Okay. So this is the picture inside V. Yeah. Now if suppose to the contrary, so the proof is suppose to the contrary, that all the functions in S actually vanish at g hat, then this would imply that actually all functions vanish on the whole orbit, on the whole of this orbit, because if there were some function which, for example, did not vanish there, you can apply it, translate that function by applying some sigma inside g, so that in the new function that non-zero value is here, but that is going to contract. So it means that all functions would vanish on this, and then because the functions in S are homogeneous, because it's a part of the homogeneous coordinate ring, it would mean that all functions would vanish on the cone of g, in the cone of g inside V. Okay, that is, from every point you take a line passing through the origin, but this cone of GG is actually dense inside this. Okay, that is because the orbit of g in this is dense inside this. Yeah, because this is actually GG closure, right? So because the orbit of GG of G in the projective space is dense inside this, it follows that the cone of this is dense inside this. So if it would mean that all the functions would vanish on this, so that would then immediately imply that all the functions would actually vanish on delta V G M, and that would be a contradiction. This is a contradiction because we assume that if it vanishes on all the things, then it can't belong to RVGM. Okay, so so not all the functions in S can vanish at g hat. And that immediately implies, well, okay, so now that immediately implies, now consider the evaluation map, the evaluation map at g hat. So given a function S, this evaluation map just evaluates it at g hat, and that would give you this, right? So this, because this is definitely g, this map is this invariant, because if you are evaluating at g hat is not changed by the stabilizer of g hat. So this map is this, and this
What is the evaluation map?
given any function on S, okay, you think of it as a function on this g hat and just evaluate it at g hat, that function you evaluate it. Yeah. Now obviously that is g hat invariant, because the g hat stabilizes that point. Yeah, and this thing says that the S is not identically 0 there, so this is a non-zero invariant. Okay, so it means that A star contains non-zero invariant, non-zero g hat invariant, which is precisely this.
What is S star?
Hmm?
What is S star?
Dual.
Ah, the dual, okay. Yeah.
Dual contains this invariant, which means that S also contains that invariant. Okay, so this is the trivial part. Yeah.
Here you use nothing about what the stabilizer is.
No, nothing. So that's why this is the trivial part.
To go from S to its dual, you use it as stabilizer.
It's reductive.
Oh yeah, you use reductivity.
But if the stabilizer is 1,
Hmm?
if the stabilizer was the trivial,
Yeah, you would still get. So that is why this is the trivial part. Yeah. Okay. Yeah, you only use reductivity of stabilizer so far. Yeah. So now we come to the non-trivial part. So for the non-trivial part, we will need some definition.
There mod out by.
So you can think of those as they are just polynomial functions on that affine cone delta tilde v vgm, just polynomial functions on those. Okay.
Yeah, but what is the fact that it's actually a representation?
What?
But it's a representation. It's not just any collection of functions.
Yeah.
It's all polynomial function on this cone.
So on this cone, it's all polynomial functions.
On which the group is
acting, so it is going to be a
What does lambda determine in this
Irreducible
irreducible representation.
No, I know, but if I tell you this lambda, then I tell you another lambda. Which polynomial
know
functions live here and which
But it
polynomial?
can be lambda. The lambda can occur more than once.
Yeah, but let's say it's an irreducible.
Yes.
So which polynomial functions occur in some irreducible representation and which occur in another?
No, that is I mean, which that decomposition is a hard part, of course.
Yeah, so there is no.
There is no obvious.
See which.
The definition is that if you take the convolution with the character, you get 0
Yeah.
or not.
It's a labeling of irreducibles right now. This one.
Yeah.
We haven't
I mean,
used
think of
anything
all-
beyond that it's a
Hmm?
labeling.
Think of all polynomials in two variables, homogeneous polynomials. They break into homogeneous polynomials with a given degree, and then change a variable SL2 acts on that irreducibly for a fixed degree, but in the general case, it's much more complicated.
Okay.
You settle a variable.
Okay, good.
Okay, so for the non-trivial part, let's make the following definition. Non-trivial part. So let Z be SLLC. This is equal to G representation, finite dimensional. Then definition, and this is due to Hilbert-Mumford. So we say that Z belonging to Z is stable with respect to G action if the orbit GZ is closed in V, is closed in Z. So that is to say, if this is Z, this orbit GZ is closed there inside it. Okay. Now this is a non-trivial thing because generally the orbits are not guaranteed to be closed. They are so-called quasi-projective varieties. So let me give some example why the orbits need not be closed. So for example, let's take Z example. Let's take Z equal to the set of m by m matrices, okay, on which G acts by adjoint action. So what that means is, given a matrix A, and if you are given sigma belonging to G, that is mapped into A sigma inverse. Okay.
So G is SLN.
Yeah, G is SLN, SL. Yeah. Okay. Then Z belonging to Z is stable if and only if it is diagonalizable. So for example, take this matrix 1 1 0 A. This is not diagonalizable matrix, and on this, if you take the adjoint action of this torus T 0 0 T inverse. If you take the adjoint of this will turn out to be 1 A T square 1 0, and then as T goes to 0, this would actually go to 1 0 0, which is obviously not in the orbit because this is diagonal. This is diagonal and this is not diagonalizable. So the thing is, the orbits can contain points, the limit points which are not in the orbit, and so the whole point is yeah. So the point is that orbits now the orbits can, such pathological things can happen. So the thing is, the things are stable if such pathologies don't happen. Now one can show that most points in Z are actually stable. By most you mean the density of non-stable points is actually 0. Yeah, but the point is, the non-trivial question is given an explicit Z, explicit z in this, is it stable? So the situation is very similar to what happens in complexity theory. Most functions are hard to compute, but given that is what we are worried about. Given permanent, the whole point is permanent hard to compute. So actually this situation, but the thing is that this proof is so called naturalizable because it works for most things. So it doesn't work for specific things. And Hilbert actually realized this natural proof barrier in invariant theory in the beginning of the last century, where he realized that, well, this is a phenomenon which most things have, but to show it for a specific point function is a very hard thing. And then he came up with the notion of a semi-stability, which means that it does the orbit contain 0 as a limit point. And he came up with a criteria, the semi-stability criteria for proving whether the specific z's are semi-stable or not. And that criteria was then extended by Mumford in the positive characteristic and fairly in a fair generality, and by came further. So that gave rise to all these Hilbert-Mumford Kempf criteria of stability. Now we don't have to go into what Kempf criteria of stability. But the importance of this is that in a sense it breaks the natural proof barrier in this setting, that this would allow you to show that the specific things are stable, and using this one can show the following, that for that, so this is shown in GCT1, that the point g hat equal to determinant of y is stable with respect to g equal to SLY action. And it is important here to take SLY, because if you took GLY, then obviously it is going to contain 0 and it is not stable. Yeah, so that is why we are taking SLY now. So what that means is this orbit g hat is closed in V. So that also means that g hat is an affine subvariety of V. Yeah. So now let's resume the non-trivial part of the proof. Where is the theorem gone?
What about the permanent?
Huh? Yeah, permanent also the same. Same. Permanent is also stable.
That's easy to check with the Mumford criteria.
Yes, a Kempf criteria.
And the lift also?
Hmm?
The lift is also stable?
Excuse me?
The lift, when you homogenize determinants to make it.
No, that actually is unstable.
Okay.
That is unstable, and that is actually going to be the so lot of work is to get over that. It is unstable, but its so-called stability flag can be determined explicitly. Okay. So now, so the proof of 1, the non-trivial part now. Yeah. So suppose S equal to V lambda G contains, oh yeah, and this uses the stabilizer of determinant. Yeah, because yeah, you were asking, right, where the stabilizer. So it doesn't use the fact that the determinant is completely characterized, but that it has a fairly large stabilizer is required, because Kempf's criteria requires that the stabilizer not be contained in proper parabolic group. So that is suppose this contains this invariant, and then the goal is S belongs to RVGM equal to RVG. So this is what the goal is. That is what we want to show, right? So now the point is, Gg hat is a affine subvariety of V, and it is also Gg hat is also contained in that cone delta V Vg, right? And this is also a closed, so it is a closed subvariety of this. That is what that thing. So now we know that this G hat is a closed affine subvariety of that cone. Yeah. So that this is the picture we have. This is now a closed subvariety of this. Yeah. So now RV of G is the coordinate ring of this. Yeah. And let us denote the coordinate ring of this as this. Then because this is a closed G subvariety of this, yeah. So what we will have is that by the general basic algebraic geometry we will have a surjective G homomorphism. So now we want to show that S belongs to RVG, and this is surjective, so it suffices to show that X belongs to this. So it suffices to show that S belongs to this coordinate ring of this variety. Yeah. But now the point is, if you look at this G hat and this is this orbit, then this orbit is isomorphic to G mod L, where L is equal to the stabilizer of G hat, right, because it is the quotient space of this. So you can this is the same thing as the of this quotient space G mod L. So now what we want to do is the explicit G module structure of this quotient space. Yeah. So for that, what we first we recall that this is equal to actually summation all V lambda G star V lambda G star, and this is by the Peter-Weyl theorem of representation theory. Tells you that, and that is basically the algebraic form of the harmonic analysis on the unitary group. Yeah. So that tells you that, and now yeah, yeah, as a bimodule, yeah, as a bimodule. So now the point is,
this is for G itself, for SL2, for SL, this is for SL.
yes, that all the
So the module is what is the?
this is the all the polynomial functions on G.
Right, the direct sum over
All lambda V lambda G tensor, this because you have the action of, it's a bimodule, G acts on itself on the left and from the right. So as a bimodule it decomposes like this. Okay. And then the point is, now the polynomial functions on G mod L, you can think of them as the polynomial functions on G which are constants on the cosets of L. Okay. So what that means is that this you can think of as Cg and the invariants. So these are the invariants in Cg with respect to the L action, because that is what these polynomial functions on G which are constants on the cosets of L means. These are the L invariants in Cg. So what that means is that C of G mod L is equal to C G L invariants, which is summation lambda V lambda G tensor V lambda G star, and then you take here, you are taking the right action from this, the invariants in this. Okay. So from that it follows that V lambda G occurs in C G L, which is equal to whatever we wanted, C G G hat.
So that's the invariant. So this
Yeah,
will give you
yeah,
the invariant.
yeah. If and only if V lambda G star contains an L invariant, which by reductivity is the same thing is that V lambda G contains an L invariant. Okay, which is what we wanted to show. Yeah. So that if S contains an L invariant, it occurs in this. Okay. So basically the non-trivial part is basically two things, is stability and Peter-Weyl.
Where was this fact that it was closed? That
Yeah, here.
It was closed. That was
Here, because otherwise it won't be a surjective map. Yeah, yeah. So it is stability plus Peter-Weyl. So that proves the theorem 1 and theorem 2 is similar. Yeah.
So you needed to know that the stabilizer is not contained in a parabolic.
Is not contained in a parabolic separate. Yes, yes.
This one.
That one can show. Yeah, yeah.
Check. That's why it's not true for this lifted term.
That's why it is not true. Because it is obviously contained in the parabolic. Okay. So now what about for the lifted permanent? What can you show? Okay, because we also want to know for the lifted permanent what is the case. Now we can't prove something as tight as that, but we'll prove some generalized form which is a relaxed version of this.
But you know it's not stable.
It's not stable, but still one can prove something, because it is though it is not stable, it is also not very far from stable. I mean, you know, one can, yeah. So the theorem 2, that if V lambda G belongs to RV F n m star, where this F is equal to H phi equal to lifted permanent, yeah, then one can say the following, that the length of that partition lambda is less than or equal to n square, yeah, and then if it is less than or equal to n square, one can also think of it as consider now the Weil module index by that lambda, okay, of H now, yeah, then this contains H hat invariant. Okay, and conversely, if V alpha H contains H hat invariant, then there exists lambda this. So we'll define this, which this says that lambda lies over alpha, and we'll define this. There exists such that V lambda G belongs to RV F n m star, where lying over means the following, where lambda over this means the following, that first the length of lambda is less than or equal to n square, and B, V alpha H occurs in V lambda G as an H submodule. Okay. So now there is a leak here. There can be lots of such lambdas lying over a fixed thing. So there is a leak here. Now, so there is a leak here. So when m is equal to n, so this theorem 2 becomes theorem 1. Okay, because then this becomes completely tight. Then theorem 2 is equal to theorem 1. So this is a generalization of theorem 1 when there is that leak. But
What does lying over mean?
okay, so lying over means that this is a weight of G, highest weight of G, this is the highest weight of alpha H. So that means first of all the same highest weight when restricted considered as a highest weight of H, then that actually, so then when you think of this as an H module, then V alpha H actually occurs in it as an H submodule, and plus the length of this is less than or equal to n square. Okay. These two conditions. So first of all it has short height, and when you think of it as an H module by restriction, then V alpha of H occurs in it. So that is what it means. So this is what pictorially this, I mean, you know, the lambda lies over, but there are lots of lambdas which can lie over that alpha. So that is why there is going to be a leak. And okay, so the proof of this, so we are not going to go in, so the proof of this again is stability plus stability of permanent, not lifted permanent, plus Peter-Weyl, and plus some technique Borel-Weyl, the parabolic induction kind of thing, which can be lifted to this kind. So we won't go into the proof of this because the basic idea is here, and then you use just the standard machinery of algebraic geometry representation. Okay, so now we are ready to prove the weak form of the Sharpe versus NC theorem.
How do you control the lengths?
Hmm?
The one thing that's different, how do you control the lengths?
No, for the Sharpe versus the
In this theorem.
How do you prove length lambda less than n squared?
I mean, when you
how do you control? Oh yeah, that is that Borel-Weyl kind of, because the thing is,
it's explicit enough that you
yeah, you can do that, yeah. Okay, so now as we said, this theorem is there is a lot of leak here, but still this theorem is, and this is good enough for us to prove the weak form of the Sharpe versus NC problem. Okay, so now the weak form of the Sharpe versus NC problem. So yeah, so let's remember what that form was. So what was that form? So it says that for any m greater than or equal to n, there do not exist b and c belonging to m c, and a polynomial e w0 wm such that permanent of x times z to the m minus n equal to g of b y c, where g y is defined to be e trace y to the 0 trace y trace y to the m, etc. Yeah.
Should be it.
Hmm?
G of y. Okay, G of y. It's probably G is a bad name. It has nothing to do with G, which was the determinant.
No, but no, but I'm giving confusing names so that for a while let's think of this G. Okay, and define all the class varieties with this G. Yeah. Okay. And as was pointed out in the audience yesterday, this is equivalent to saying that there does not exist A in MMC, and again E such that permanent x z to the m minus n equal to g of you can take d, what? Yeah, but the proof technique would work for just this form, not that. Okay, so that the representation theoretic obstructions would occur when you start with this form, because here the point is that when you take just the left action of d on traces, and then the stabilizer is essentially trivial. So you are not going to get any representation theoretic information, and so the whole approach will be just grounded. Yeah. So you know, so the representation theoretic obstructions would exist if you start with this form but not with that form. Yeah. So it is a very delicate thing. You have to have the stabilizers. Yeah. Okay. Okay. So let's see how to prove this now. So we'll need. We'll need both these theorems. So okay. So we'll take here. But the point is, if this thing is equal to this, all the things of different degrees you can just yeah. So it's fine. Yeah.
Just remind me why this is the weak form.
Because you don't allow all transformations of y. It's a very limited set.
Because the thing is, in the original thing, there does not exist A belong to M.
No, linear, it was linear also before, but before you allowed linear in all m squared variables of y.
See, the basically.
So this is just B left and right multiplication.
So this is M cross MM inside. Huh?
Yeah. Using n by n, not the n vector of length n squared.
Yes, yes. Okay. Excuse me?
It's a weaker form. Seriously weaker form.
Oh yeah, of course it is. It is a weak form, obviously. But even the weak form gives a lot of trouble. Yeah. It is weak, but the troublesome still. Yeah. Yeah. Okay. So the theorem is now that there exists a family of obstructions in the weak form of Sharpe versus NC problem. Okay. So the proof. So for the proof, now we are going to let G equal to SLM cross SLM instead of SLM square, and now H is going to be SLN cross SLN. Yeah. And then you define all these class varieties, delta Vg, delta Wh, etc., delta Vf similarly. Okay. I mean, just as before, just taking this new G and this new H, and the notion of obstructions is also defined similarly. Okay. So now let us see what is the stabilizer of G hat. Okay. So the thinking of this as an affine point. So the stabilizer of this G hat, first of all, it contains Sm, right, which is embedded inside SLM cross SLM by sigma going to sigma and sigma inverse transpose. That just means that the traces are stable under adjoint action. That's all it means. Yeah. Because the traces are adjoint when you take this yeah, A inverse here. So the trace. Huh? No. So you are basically you are taking the trace of y to the m is equal to trace of whatever A by A inverse to the m. That's all you are using. Yeah, to make it an action, because you are taking on the right hand side.
So it would be sigma sigma.
Yeah, I mean it's okay, but I mean we are taking it on like this A inverse.
You don't act by right and left hand relation. So it's the action is not y to b yc inverse to start with.
No, because the thing is that B and C could be singular. So it is this BYC. So I mean.
How do you make SLM times SLM act
On?
on y?
Yeah. So basically it is a left-right kind of thing. That is why I'm. So I mean so you are taking this. Yeah. I mean you can take it like that also, sigma sigma. Okay. So okay, so now the point is the following things, that
What does it mean, the fact that you take only the diagonal there? That means that for you.
the traces are invariant under adjoint action. That's all.
I understand, but I'm just wondering if the proof that that the weak form, the proof of the weak form says that you might as well use C equals B inverse or something like this.
No, C equal to no, it doesn't use that.
Without loss of I mean, but you are taking only the
No, here-
direction.
Huh?
Only the sigma goes.
No, it's just the stable.
Stabilizer. Okay, very good. Good. Yeah, that's fine.
Okay, this is safe. So now the point is that the irreducible G modules are now of the form V alpha SLM tensor V beta SLM, and this contains G hat invariant by Schur's lemma if and only if alpha is equal to beta by Schur's lemma. Okay. And 2, the more non-trivial part is proven by Ariki and some other Japanese mathematicians. So, which says that now if you take the irreducible representation of H, which of this kind, that first on the first part, so it is SLN cross SLN, so this is the trivial thing, and the other thing you take V gamma of SLN, and where you take that the size of gamma is equal to 2 times n. Okay, so the summation of all, so this is summation of all gamma i's. Then from the results it follows that this contains.
Sorry, I'm not sure. What do you take? What representation do you take? You take identity on the left and then
tensored with V gamma i. So this is a representation of
V gamma.
any gamma V gamma SLN where gamma has size 2n. So take irreducible representations of SLN cross SLN of this kind, trivial times this. Then from the result it follows that this contains H hat, that is invariant, that is this is the stabilizer of the permanent if and only if gamma is divisible by 2. By that we mean that gamma is this partition, right, gamma 1, gamma 2, so all the things are divisible by 2. Okay, so that follows from their thing. And C, by the classical Pierre's rule,
Does this correspond, does numbers correspond to some combinatorial property of the permanent that we should?
no, it is a representation theoretic property of the stabilizer.
I understand, but we understand the stabilizer of the
Permanent, yeah.
just diagonal matrices. So
No, diagonal and the symmetric and the permutation, that is the
permutation. Sorry, I meant.
yeah. So
Why does this evenness come in? I mean,
why does it?
the even. I mean, somehow.
No, so it doesn't correspond. The proof is completely representation theoretic, so it doesn't really.
But it says it's a statement about the permanent.
Permanent.
Right? I mean, it's a clear statement about the permanent. It looks very combinatorial because you talk about this. So the representations of the symmetric group are given by these partitions. You say that somehow these even partitions play a
Correct.
role.
Yeah. That it contains an invariant with respect to that. That the point is, this is in general a very hard problem because.
Do you know what this invariant is?
What
The invariant is a polynomial.
No, the invariant, they don't actually calculate the invariant. Actually calculating invariant is a very difficult thing because the whole thing goes through character formulas. So it's not actually going to tell you what the invariant is in that. It's just going to say that the invariant exists. That's it.
I understand, but so it would be an extremely useful thing to understand this invariant. So it's a polynomial function on the entries of a matrix, which do not change the permanent when we.
No, it's not a
transformation.
No, it's not a polynomial. It's a while module of this SLN. So it's actually the polynomial function on the orbit, not on the. I don't know. I mean, you can't. You are taking it on. You have to take it on the orbit of the permanent, not on the matrix entries. So you can't just convert into something about permanence easily because it is actually talking on the orbit of that permanent and so forth. Yeah. So you are talking about polynomial functions on the orbit of the permanent. So I don't know if you.
I'm confused. Invariant means that it's invariant on the orbit. It's a function of the.
No. This means this contains an invariant with respect to that stabilizer. This contains an invariant. That while module contains an invariant. So the space of so corresponding to that there will be some space of homogeneous functions on the orbit which contain an invariant. But that is a highly non-constructive. I mean, all these proofs are highly non-constructive. So you can't really.
Instead about computing the algebra of function on the orbit space H modulo T stabilizer.
Yeah. Yes, yes, it would tell you about that H modulo the stabilizer. In that thing there exists an invariant of that, yeah. But you can't really nail it down because the proof is character theory. Whatever, okay. And the third part is no V alpha SLM tensor V beta SLM with alpha equal to beta can lie. So, one can define the definition of lying over similarly, lie over this 1 gamma V gamma SLN if you take this gamma, if gamma 1 equal to n by 2, gamma 2 equal to n by 2 and the rest all 0. So, this one can do just by the classical representation theory, some branching rules. And then the proof just follows by putting this and the analog of this theorem, the theorem 1 and theorem 2, and just you put everything together and then yeah. So, this follows from then. What is what?
Which paper is it?
So, I can show it to you, yeah, because the thing is in general that is a plathism problem which is very hard, but for special classes of thing they actually find the things. So, yeah, I will show it to you.
So you feed these into this.
All these,
normal
yeah,
calculation.
and then you just feed it into this technology and then A, B, C and plus theorem 1, the analogues of theorem 1 in this case and theorem 2, and this implies the result, yeah.
So classically,
Hmm? Excuse?
pointing out that this is really a classical invariant theory plus these effects in combinatorial representation theory.
Yeah, and the stability, yeah, only stability, and also stability is
And the stability, but you only need it over complex numbers.
yes, here the result is conjectured to be true over arbitrary fields, in fact, of characteristic different than 2, but and the stability part would work by Hilbert-Mumford's work or arbitrary, positive characteristic also. What would not work is the Peter-Weil theorem. I think that is where the complications start, right? Yeah, you will not get in positivity characteristics, the Peter-Weil will not hold, and then I think then you have to worry about representation theory in positive characteristics, and I suppose the thing can be carried out, but it would be a gory affair, yeah. And so the main chunk, the stability part works actually. It just Peter-Weil which is a problem. Okay. So what I was saying is if we need a break of 5-10 minutes, we can stop or we can continue.
You decide. So
No, I am fine, but huh?
At least 2-3 minutes.
yeah,
Oh, okay. Huh?
7 minutes.
Now starts actually the real grind after this. So, now how to go from the weak to the general. So, there are two problems here that have to be addressed. The first thing is fix the leak. So, this leak is this.
Question about the proof of the weak form. Do you actually find the D,
Huh?
the degree for which the obstruction occurs? How explicitly do you get the
Oh, yeah.
you know,
yeah.
for which D?
Yeah. There degree whatever 2n whatever, yeah.
2 answers,
Yeah.
yeah.
Okay, fix the leak. So, this is what we mean by the leak. Yeah, this is the leak. That there are what happens, there are too many lambdas lying over the same alpha, and in general one can in fact show that for small cases like for alphas there are so many lambdas that it generally contain an invariant with respect to the determinant stabilizer. So that is, this kind of thing is not going to really help you much. Okay, so that is the first problem. Huh?
What is now the stabilizer? So you're no longer looking at action by B times C, but by mixing all the coordinates.
Yes,
All
yes.
the
It's n squared.
n squared, the n squared coordinates, and now your big group, so your ambient group is huge.
Yes. So basically now we have to show that such that permanent of x times z to the m minus n is equal to determinant of a times y. Yeah, when m is equal to 2 to the log a n a fix. This is the general thing now. Yeah. So the thing is, earlier they were like m square n square 2m square degrees of freedom. Now it is m to the 4. Okay, so it is much bigger, and those BC are very special kinds of transformations. So it is so one can imagine that from here to here is is the real thing now. Okay. Okay, and so first you have to fix the leak, and then what you need are the efficient criterion for the following two problems. Does V lambda G contain G hat invariant? So that is what is required to, for example, use that, right, for V lambda, like which modules occur in the homogeneous coordinate ring for the determinant. So would require this, yeah, and similarly for
The leak is something you impede because we imposed x to be a small part of this bigger matrix, which was somewhat artificial.
right, and yeah, and then there is this tail here, right, because of that. Because of that there is a big leak there, yeah, and
You have to do it somehow. It's not clear what. You have to do it somehow.
The natural data is the system of linear form you want to put into big matrix,
Yes.
I think, from the small one. And it's a little artificial to do.
But do you think there is a more natural way to do it?
what?
No, it's possible. Yeah, you do it in a particular way. The embedding of the n by n matrix in the n by n matrix. Maybe there's.
No. I mean, the leak is a serious affair. I mean, I think.
No. I agree. We agree it's a serious affair. I just wonder if different embedding of the n by n in the n by m would make it a little.
Is there? No.
I'm sure it's not.
And does V pi of H contain H hat invariant? So this, the fix the leak, we are not going to talk about, not today, because we are going to talk on this part. Huh? No, I mean, because until this is understood, the plan for fixing the leak depends on the solution. I mean, the proposed way of going this. And first we have to understand this for fixing the leak. So we are going to concentrate on 2 and see how far we go. Yeah. Okay, so
Now, G is SLM square and 8 is SLN square.
yes. So both A and B are special cases of the following. A and B are special cases of the following, the subgroup restriction problem. So let's say that we are given a reductive H explicitly, as we have in our cases, we know what it is, yeah, and that it is embedded inside G, yeah, which is either GL of V or it could be SL of V, doesn't matter, yeah. I mean, the thing are the same, where V is an explicit representation of H. Yeah. So so the one important thing that we'll be interested in is the Plaithism problem when H is equal to actually GLN. Now this n is different from now the thing so far. Okay. Yeah. So this GLNC inside G equal to GLV, where say V is equal to the representation of H with partition mu. Okay, so it is given explicitly. So this is homomorphism map has to be given explicitly. So in this case, that homomorphism map can be specified by simply specifying mu. Okay, so we are given this subgroup restriction problem.
What does n have to do with V?
Huh?
What does n have to do with V?
No, the V is any irreducible representation of GLNC. Okay.
Okay.
Yeah. Now, so now you can think of V lambda G as an H module via this map. So then by reductivity of H, this would split as V pi, where A lambda pi, and we can say rho V pi of H. And in the case of Plaithism, we can just denote this by V pi mu, because rho is completely specified by mu. And these are then called the Plaithism constant. Yes. So given a big module of the big group, split it as a small group and take the multiplicities. Yeah. So now the problem is the following. Now the complexity theoretic problems that we are interested in the context of those A and B. Yeah.
Rho is mu?
Yeah, rho is mu.
Huh?
Yes, so there is A lambda by rho. Rho is mu.
You just call it rho.
Yeah. So for general reductive thing, this rho would be specified by something, and in the case of SLN, that rho would be specified by just mu. Yeah. So those are. So now the problem now is, say in general, given lambda, pi, and rho, or in the case of Plaithism mu. Okay. The question is, does V pi H occur in V lambda G? That is the Plaithism coefficient A lambda pi rho greater than 0? Okay, so this is the question. This is the complexity theoretic question, and these are actually just the special cases of this. For
4 pi equals to,
huh?
4 pi the trivial.
For pi trivial representations and H being the reductive group as there. Okay, so this is precisely, so this is the first problem, and for this in other thing is we want to find a positive, that is, by that we mean some polyhedral formula for A lambda pi rho, and by that we mean, so what we want to show is that this A lambda pi rho is equal to the number of integer points in some polytope P lambda pi rho, some explicit polytope, for some polytope P lambda pi rho of polynomial in the description of that polytope. So this in the case of Plaithism problem would be this. So these are the bit lengths of the various partition. So the of this much poly bit size description. So this is an important thing from the complexity theoretic point of view, that the description of that polytope, yeah, should be should have the complexity that is polynomial in the bit lengths of lambda, pi, and mu. Now this is what makes this problem hard. So let us see why the traditional technology of representation theory is not going to work, because
When you say that this is important to have this polynomial in the bit-size description,
yeah.
this is important for what? I mean, would the proof, I mean, the proof necessarily, the proof could work with any representation.
No, but when you
with any, sorry, polytope So it's because of your problem checking that the polynomial
Yeah.
in some cases.
Yeah. So you need a nice small dimensional thing, okay, and the way is if you go about it in a natural way, it would automatically be polynomial dimension. I mean, this would happen automatically, okay.
Okay, it's not of any significance to being able to carry out the proof. It makes good. It makes sense. We may understand it better if it's low dimensional.
But it is required in the way we go about it, in the approach, that that the polytope be small dimensional.
It's required in what sense?
No, because finally we have to check that one polytope is non-empty and one polytope is empty.
But
So
you don't. I mean, you just prove that one is empty.
yeah. But the whole plan is
You don't run an algorithm on it.
no. But you have to actually look at the constraints and all that, and the whole process would become much more complex if the dimension of the polytope.
He's asking a much more basic question. You're going to write down some conjectures
Yeah.
which are going to imply the result. And he's trying to say, why is the complexity of this question here, which needed in the before you there was no issue like this.
Yeah.
You
There.
just proved the existence.
Yeah.
Here you're going to try to find the lambda which distinguishes, like you described in the first lecture. I guess at some point you're going to try to find a certificate.
Yeah.
Prove there exists a certificate, but you don't need to produce it.
No, you don't need to produce
So
it.
why? So his question is a fair one. Why we have to worry about the complexity of this at all?
Because I mean, we'll see that, for example, in the existing, when the polytopes exist, like for example in the case of Littlewood-Richardson and so forth, all those whenever the thing works, like you want to show the proof that the dimensions are actually polynomial, and we want to mimic whatever is actually currently working. That's all. I mean, you know.
So I'm very happy with the fact that complexity theory enters the proof, and in fact, but you know, it's just the way it works or the way you like it to work. It's not that it's the only way it would work.
No, we are not saying that this is the only way.
It's not essential. I mean, if some mathematician decided to prove your conjecture, they wouldn't be restricted by this particular thing you wrote on the board
The polytope is important. They would have to come up with a polytope.
Any dimension.
No. In general, like if you are given this number, you can of course always come up with a polytope of exponential dimension that is equal to the number of integer points in that. I mean, you can always, but you have to have some additional constraints on it, which we'll specify in a moment. And once those additional constraints are put in, then though you don't really have to say this, but the intuitive claim can't be formally proven is that this kind of thing would happen automatically on the basis of the existing.
But you also want that if you replace lambda and pi by some multiple,
Yeah, homogeneity. So we'll require that to be. So what we'll want is that some stretching function associated with that should be the Erhard quasi-polynomial of this in some.
In the previous example, what is the polytope?
In the
Sariki, what would be the polytope?
Yeah, so in the polytope would be that lambda 1 is greater than or equal to lambda 2, you know, and so there are two things that there was this V alpha H tensor V beta H, and this contained an invariant if and only if alpha was equal to beta, correct? So it means that there will be two constraints, alpha 1 greater than alpha 2, etc., and you know alpha 1 equal to beta 1. So just this trivial inequality of this partition, that's all. So that would be the polytope. I mean, you can see that it is a polynomial dimension and so on.
now for the determinant, your subgroup is almost connected, this stabilizer, but for the permanent, it's a big disconnected thing.
But that disconnected thing by that result of Ariki can be converted into a connected problem, to the Plathism problem actually. So though it is disconnected, actually it can be converted. So those coefficients can be written in terms of some positive formula. So they give that explicit formula actually in terms of the connected thing. So finally we are back to the connected case. Yeah. So the point is that if we use, like for example, the character formula, like Weil character formula or all kinds of character formula, we can't use that kind of technology because the character formula first of all will have exponential number of terms and they would have all the alternating signs. So decide whether that formula, that character formula is going to vanish or not is a pointless. So what you really want is a positive formula, so that looking at that formula, then you can decide whether this is going to occur or not. So this is really, that positivity is really, so this is really the key thing that we require. We require some.
Let's repeat, it's a positivity, not the complexity.
Okay, yeah, okay. Okay.
It's just because Avi does raise we want to know what sort of is critical and what is motivation by you.
Okay.
So all the complexity considerations are basically a heuristic that you're using to search for the proof,
Yes.
not a necessary property of the proof.
Necessary property, it is more or less required for this approach, but one cannot say that every approach has to have it. Of course, one can't say such a thing, but that this particular thing, the way it is going, it is kind of, these things are falling, kind of getting ensured automatically. That is what it is happening on this way. But one cannot say there can be some other way where this is not happening that way. But
Positivity means strictly positive. Means you also still need to know that there is a point there, right, to get something strictly positive to proceed. I'm perplexed by
That's this dilation will allow you to do.
I'm just trying. I assume that will come right.
Yeah.
Say positivity. You don't mean. You mean that these are given by the number of points.
in integer point.
Number is strictly positive, right?
Yeah.
Not zero.
No. What do you mean? I mean, if this is zero, then of course.
It's like if you have a formula, what you're calling positivity is a combinatorial realization of this coefficient.
Correct. As the number of integer.
Not as an alternating sum, but as a sum of positive terms.
That's all. So that positivity is the crucial fact. Yeah, is the crucial property that would be needed for us.
So this is a problem in many kinds of. This is an issue in many problems in representation theory.
Oh yeah. Of course. And so that the same problem is occurring here in a way is reassuring that complexity theories want the same thing that mathematicians also want in some sense. I mean, right? Yeah. So, and the other thing is that the dimensions of these are exponential in lambda and g, and that exponential in the bit length of lambda and the dimension of this. So if you try to do anything with the representations, or you try to compute the character formula, the whole process is going to be really extremely complex. So that is the main. Okay. So let us first understand the one case that is completely understood, and that is going to be the basic prototype of how we are going to go ahead. So the completely understood case. Completely understood Littlewood-Richardson case. So this is given by H equal to GLN, that you put it into H cross H by sigma goes to sigma, that just the diagonal. So this we can also call this the diagonal case. Yeah. So in this case, the representation of G, just the tensor products of the representations of H. So it would be V alpha H tensor V beta H, and then that would split as C alpha beta lambda V lambda H, where these are the Littlewood-Richardson coefficients. Okay. So in this case, we
reverse the sides of the equation, so as the object on the left is in H. So alpha beta is a pair. That's a representation of G. On on the left-hand side of the equation, you have a representation of G, right?
Yes.
The tensor product. You just reversed this.
No, no. No. What?
Yeah.
So
You
V
have a
alpha
representation
tensor
of
V.
G on the left-hand side,
That's
and
right.
you decompose it into a representation of the
H
small
on the
on the
yeah,
right-hand
that's
side.
right. Okay. So you reverse two sides of the equations.
No, anyway, whatever. Okay. Hmm? Okay. So then, first, this is the classical thing, Littlewood-Richardson. So this gives a positive formula for those coefficients. So let's not worry about the complexity. Let's just concentrate on the positivity as AVN. Okay. 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 So that, I mean, we all agree on positivity, right?
Yeah.
Okay, good. Okay. So let's just stick to positivity. So then there exists p alpha beta gamma, okay, of the bit length in this case is, I mean, you can ignore these brackets, but it is true, of bit length polynomial in the bit lengths of alpha beta. So you can see that it happens here naturally, yeah, such that if you take the stretching function associated with this C alpha beta lambda, so first of all this is equal to the number of integer points inside P alpha beta lambda, and moreover we have that if you define the stretching function C alpha beta lambda k equal to C k alpha k beta k lambda, okay, then that is equal to the number of integer points in k p alpha, so beta lambda, so which is so what we are, so if this is p, then this is what we are calling the Erhard quasi-polynomial, yeah, of this polytope. And by quasi-polynomial, let's remember that f of k is called a quasi-polynomial, if there exist polynomials f I k where I is less than or equal to L, such that f of k is equal to f of I k if k is equal to I modulo L. Okay. Periodic polynomials, yeah. So that is the first part of this. So that is classical. Then, so this is the saturation theorem of Knudsen and Tau. So which says that C alpha beta lambda is not equal to 0 if and only if this polytope P alpha beta lambda is not empty. Okay, so that if it is not empty, it always contains an integer point. So that is the saturation theorem. And using these things, then it is an easy observation that given alpha beta lambda, whether C alpha beta lambda is greater than 0 can be decided in polynomial in the bit lengths alpha beta lambda time, and this just follows by linear programming, because once you know that, you have to just check whether this polytope is non-empty or not, and that you can just do in linear by linear.
You have brought into this issue a
No, I mean let me put a big bracket there, but I mean we are going that.
We're just trying to follow logic.
Okay. Okay, so now
I'm trying to understand the saturation theorem. Formally, you said that this coefficient is the number of points in this polytope. So
yes,
what is the saturation
but
you say?
that if that polytope is non-empty, meaning if it contains any real point, rational point, it actually contains an integer point.
Or if multiples contain points, then there will be already.
Okay, so
now
the
multiples
claim
don't
is
need
that the polygon. Okay, so it's
saturation, because you don't
so-
need to take multiples.
Yeah,
Saturates immediately.
Yeah.
but okay, and this is something you need to use.
No, I'm just
Just an example.
That's fully understood.
fully understood case. Okay, I mean this is what we are taking as a basic prototype for our thing. So of that, those who are interested only in the positivity can only worry about this, but the complexity may want to look at the.
understand why you're so interested in that in this
Okay.
context of completely.
Okay.
Where one can read Littlewood-Richardson in that language.
In that language, yeah, it is. So, for example, in GCT3 is given in that language. Also in, yeah, I will, and also in like Knudsen and Tao's thing in terms of high polytopes and. Yeah. Okay, so now this is the basic prototype, and now we want to lift this story to the Plathism. Now, if you are just interested in positivity, the first thing that you need is that an appropriate stretching function associated with this has to be a quasi-polynomial. Otherwise, the polytope is simply not going to exist. Yes, because we want that. So let us define the stretching function associated with for the Plathism problem. Plathism. So let's define. So let's take the Plathism problem. M lambda pi mu k. Let's define it to be a k lambda k pi and mu. This mu does not change, okay, because in the Plathism problem that mu is what specifies that homomorphism from H to G, that is kept fixed, and the weights of G and H are now varying. Now, so the Kirillov's conjecture was that this is a quasi-polynomial. Actually, it was weaker than this, but a stronger form of his conjecture. Now, this is the minimum that you need if we want the polytope to exist, because what we want is that this should come out as the number of integer points of some polytope, and if this is not true, then we are in deep trouble immediately. Okay.
Which conjecture is this?
Kirillov's conjecture.
And this is in what generality? In this generality?
No, it was made for that.
Any morphism of reductive group?
No, it was proved for that, made, but it is proved now. In GCD6 is proved for any morphism from reductive to G.
What was the conjecture?
What is the conjecture?
The conjecture was that this, so the exact conjecture was the following.
If it's proved, I didn't know it was. So if it's proved, why don't you just say what the theorem is?
Yeah. The theorem is that it is true. Yeah.
It is true.
What is to
Huh?
What is true? For which? For which?
This is a quasi-polynomial in this example.
For what groups?
For what groups? Yeah.
So, for example, in the Plathism case, it is true,
Okay.
and also for any connected representation of H. So, when you take H as any connected reductive group, and V mu H to be any irreducible representations of this.
Or you need to map to GLN. You cannot map a reductive group to another reductive group.
So this particular the thing that I am going to talk about would work for that also. Yeah. So, but
This is proved by you, right?
huh?
Who's proved this?
Whose?
You're saying.
Oh, this is proved in GCD6. Yeah.
Are you proving
You
it?
call
Yeah,
it a
yeah.
Kirchhoff conjecture.
Yeah.
In general, you're saying.
Yeah. In general. Yeah. Okay. So let us go there. So this extends an earlier the idea of Bryan, where he proved quasi-polynomiality of Littlewood-Richardson things, and it extends to the Plathism thing. So the proof. So the theorem. So we'll just state it for the Plathism, but it works in more generality. But we are just going to do it for the Plathism. That m lambda pi mu k is a quasi-polynomial. So this is a critical result for our story. So let's go over that. Yeah.
Okay, so it's this embedding of GLN into GLN cross GLN, and you take it's
Huh?
those exact coefficients.
Yes. Those. This exact. Yeah. So if you
Just
take.
as a matter of interest, the periodicity L, can that be
Huh?
sort of exponentially large?
Excuse me.
How big can L be?
The period.
In your
It can be exponential. Yeah.
and that's not an issue?
That's not an
Knowing
issue.
something's a quasi.
No. It's not an issue.
We'll see.
Yeah.
If the period is so large that you never see it in this world, then it's not periodic.
No, but the
You'll see how you use it.
no, we don't use the period or anything. Yeah, okay. So
What does it mean to be quasi-polynomial?
no. Of course, we'll show that there is a period. Of,
There is a I mean, there can be a polytope of polynomial dimension.
And-
for
and-
which the period of the number of points.
Yeah, but if he's ever going to use such a statement, then
No, it's
should
just
the size of
using
the period has
non-empty.
to
It's
be
just
equal.
using
No,
non-empty.
it has to be convinced there could be a polynomial.
Ah, okay, well, that's...
no. We don't need the period. The periods are always going to be exponential, and that doesn't matter.
Okay, if what Deline says is, this is just motivation because you're going to prove a much stronger theorem than that, you're going to prove the positivity.
No. That polyhedral thing we are not. Just quasi-polynomials. What?
So this is
there
your
are
hope
parts
is
of-
evidence
yeah.
for a positive.
Evidence for the polytope thing. And then the conjecture is going to be that there is a polytope whose errad quasi-polynomial is there.
Yeah.
Okay. But to make that thing, I mean, we have to first prove this. Okay. So
For the positive, he wants positivity. But
okay. So
he gets positivity.
so let us prove this. So the proof. So let V be equal to V pi of H. So that is that. Okay. And we are taking that H, we are taking to be GLNC, though it is not really required, but we are. So now let V equal to little pi inside belonging to V equal to V pi into the projective space associated with this be the point that is stabilized by the Borel subgroup of H, which consists of all the things which lower triangular things. Okay, and so this is the highest weight vector. This is the highest weight vector of that. Yeah. So in that case, the orbit of H of V. Yeah. So inside PV is already closed. Yeah. So it is already closed, and so I mean, and this would be H mod some parabolic thing of that, and so in that case, so this is the same thing as what we have been. So this would be the orbit closure would be the same as the orbit in this case. Okay. So this would be the same thing as HV, H equal to H bar V, and then we are letting RV of V to be the homogeneous coordinate ring of this. Yeah. Now this is of the form V k pi H star over all k, and that is Borel well. That follows from Borel well. Huh? Yeah. So the thing is that, so now let's take the affine cone of this. Yeah, so this affine cone would have a singularity here, correct? And then this Kempf shows that the singularity, that this has rational singularities and normal. Singularity Kempf. So for complexity theory, so what rational singularity means is that there is a general procedure of given any variety that it can be, all the singularities can be resolved, and there is a procedure by Hironaka for resolution of singularities in characteristic 0. So given any variety with singularities, you resolve it using that resolution procedure, and to that resolution procedure by Grothendieck machinery one can associate some cohomological object. If that vanishes, then the singularity is rational, which means we are just going to think of this right now as nice. Okay. Now for this particular thing, actually Kempf gives an explicit resolution procedure, but we are actually going to use the resolution of singularities in full power in the remaining steps, though here it is not required because here actually Kempf gives the explicit resolution procedure. Yeah. Okay. So, so in that case, if this has rational singularities, in fact what we will say that this ring itself is rational and normal. Okay. So, we say that the ring is rational and normal if the variety or the scheme associated with that as rational and normal. Okay. So, similarly S equal to pi V k pi h star tensor V k lambda g is rational and normal. Again, by the Kemp's thing would tell you this also. Yeah. Now what we do is we take the ring of invariants inside this. So, these are the H invariants in S. Yeah. So, if you take the H invariants inside this would be of the form this V k pi h star tensor V k lambda g, and you take H invariants inside this. Yeah. So, this ring is finitely generated by Hilbert.
Might challenge you to produce the periodicity L in any
No, I am not going to use the
recursive function.
no, it is not important. The period is not going to be required in nowhere. Okay. So, yeah, and then the thing is, and this is the crucial part of the thing, that this actually the spec of this has rational and normal singularities, and this is the crux of the thing by Buta. So, this is the crux, that if you start with a variety with rational and normal singularities, and then you take the quotient, the categorical quotient with respect to a reductive group action, what you are going to get is a new thing which also has rational and normal singularities. And there that actually uses the full power of resolution of singularities, because these things can actually be fairly complex quantity. In our case, in fact, it would be. Yeah. Now the point is, now what is the dimension of this is precisely the multiplicity of V k pi h in V k lambda g, right, by Schur's lemma. So, this is precisely that, right. So, which is precisely what we are calling a lambda pi mu, yeah, k, sorry, a k lambda k. So, it means that the Hilbert function, so let us call this the Hilbert function of this ring S h k is precisely the function that we want, a lambda pi mu k. Yeah.
The function is itself a polynomial. It's one polynomial.
It's not. It's a Hilbert function that is takes the dimension.
Right. It's
Yeah.
one polynomial.
No, it's not a polynomial always. It is asymptotically a quasi-polynomial. But the point is, now because it is the Hilbert function associated with the things that are rational and normal, then by Flener it would follow that this is a quasi-polynomial, and this will follow by a result by Flener, who shows that Hilbert function of a ring which has rational and normal singularities, actually it is not just asymptotically quasi-polynomial as Hilbert said, but actually it is quasi-polynomial right from the beginning. Okay. So, that is a cohomologically vanishing thing, and so we get that what we want actually is a quasi-polynomial. Okay. So now we can make the conjecture, the positivity. Yeah.
So this is what Kirillov conjecture?
Yeah, this proves. So now we can make the positivity hypothesis. That there exists a polytope p lambda pi mu of, and now this I was going to state the bit length complexity, but I am going to keep that in the brackets in front of Peter, but you can imagine what it is. Okay. And such that this polynomial pi mu lambda k is the Erhard quasi-polynomial of this. And in fact, the thing is what this proof shows, okay, is that the dimension of this, whether you like it or not, is always going to be polynomial. If the polytope exists, then in fact it is going to be the dimension of this ring, and which you can then compute is going to be polynomial. Okay, so even if you don't want it, it is the dimension is coming is
what the polytope,
the dimension is going to be polynomial. Okay, is guaranteed to be polynomial if it exists. Okay, so what we are saying is that if you go about naturally, the nice complexity theoretic properties just follow. I mean, even if you don't go for it, they just so that is kind of an evidence of the naturality of the thing. Okay, so now what is the, so assuming this pH, what does it, so let's remember that I think we rubbed our original thing, but now in our context so that so what this says in our context is the following, that assuming pH, so these are the complexity theoretic consequences of this, assuming pH, whether a k lambda k pi mu is greater than 0 for some k greater than or equal to 1 can be decided in polynomials in the bit lengths lambda pi mu time, and if so, one such k can also be found in polynomial, one such k can also be found in polytime. And this then just follows by linear programming, and then the theorem that in the context of the original thing that we started, that assuming pH, that is what we wanted, assuming pH whether V k lambda g occurs in the homogeneous coordinate ring of the determinant dual for some k greater than or equal to 1 can be decided in polynomial in the bit length lambda time, and similarly for the permanent, whether V k pi h belongs to R W h n star for.
Okay, now I'm terribly confused. Why, in your first proof, you need a certificate.
Yes.
You don't need to prove P is not NP in your dream.
In
or plan.
in your
In this whole attack that you have of P equals not P, you're going to give a proof, and we hope you're going to come up not with any search. You don't go search.
no, we are going to, so basically once you get a polytope, you have to produce those lambdas and pi x.
So these are purely complexity.
Heuristics, heuristic. That
Not part of the plan.
huh?
That
No, I mean for complexity.
maybe how you found things or how you think of them.
Yeah. Okay, so the point is there is that easy procedure intuitively. By easy, by complexity theories we mean the polynomial time, and it is just not easy in theory, but also there are these polyhedrons associated with it. And now when you go about it, you have to just find those particular lambdas and mu so that one polytope is non-empty.
That's not that search is not something that is a complexity question. That's, you have to find a proof.
Yes.
So in the Richardson-Littlewood case, the polytopes are understood explicitly.
Explicitly, yeah. And in fact, then these kinds of things can be done. And in fact, what I am saying is, these kinds of questions can be in the high polytopes can be answered. So that is a basic prototype. So whatever is understood in the Littlewood-Richardson case, you just systematically want to. So now are the main questions, and now is actually the heart of the problem, which we are not.
About the complexity of the polytope.
Yeah.
Something like a convex hull of an orbit of a Weyl group. That's too complex, or is it simply allowed?
Huh? No, there's a convex hull of the orbit of the Weyl group. What about that?
Is that too complicated?
No. So from the complexity theoretic point of view, no, but no, from the complexity theoretic point of view, it is not too complicated. That's okay. I mean, that would be the kind of thing you would want. I mean, if you want the intuition, yes.
It's easy to check. It just
No, in fact, exactly, we would want something of that kind. Yes, yes, from the complexity theoretic point of view. Okay, so now, and of course, but this doesn't say, so what are the main problems? So this is actually the heart of the approach, this approach. So the following two questions: how to prove pH. Okay, so this
Give you that.
give. I would be so happy.
No, what is pH? Was a clean mathematical question. What does it imply?
No. But just this is not enough because
Yeah, that's what he wants to know. What next?
how to fix the leak. Okay. So just pH for this is not enough. You have to fix that leak.
Because with
Yeah, that leak. So for that leak, what is required? If you just give me pH, that is not enough in this approach. So that
pH will tell you that there's a point that you're looking for if there were a real point, more or less.
Yes.
You find an integer point.
No,
in
no.
Saturation or something like that, right?
Yeah. So what is
That's
required?
not enough.
Huh? Yeah, and no, for fixing the leak, what is required is that what I said in the first lecture, that you have to prove pH for those triples. I mean, you have to associate analogous stretching functions for the representation theoretic thing with the class varieties, and you have to prove pH for those things. Now, if you give me that, then of course.
But are they all just positivity or positive?
Yes. Like
That's
this.
enough? Just straights?
Yeah, positivity.
Questions about
Yeah.
interpretations?
Yeah.
Yeah, but it's about uglier objects, I think. Right?
Doesn't matter, but if they are just
No,
simply
these kinds of objects, that there are these polytopes, and if you get those polytopes finally for those things, then the next thing is the polyhedral combinatorial.
how
do you
can
know
we
that it's
falsify
not zero?
this?
Huh?
How can we falsify this? Let's say.
How can you falsify it?
Let's imagine that the approach doesn't work. How do you prove that there is no such polytope?
Well, that's your.
No. I'm saying that
I mean, I believe the approach is right. So, I mean, all these quasi-polynomial.
if you ask me how to falsify the Riemann hypothesis, I say go and give me a zero that doesn't.
No, so for example, one way to falsify this approach would have been to show that this proof is wrong and it is not a quasi-polynomial. Okay.
No, okay. This you prove.
No.
I can't use that.
No, but I am still curious whether there's no complexity issue left at all, according to
No, in a sense, yes. I mean, yes.
The issue is that to complete this program,
Yes.
you have a sequence of positivity hypotheses for these coefficients.
Correct.
Nothing else.
Yes.
And I'm still curious how you see those how you get it. I can see that will tell you whether the thing is not zero if it's non-empty.
Yes. Right.
But how do you know? I mean, we don't know what we're computing here. At some point, you look where. All right. How do you know those numbers over the reals or not? To use this interpretation,
Yeah.
you need to know that this polytope's non-empty.
Yes.
How do you know that? In other words, how do you complete the proof just under this interpretation?
No, so the thing, if the polytope is empty, you are going to find, so say that, so you have to do the similar polytopes for the stretching functions associated with, yes, so there were two kinds of those polytopes. One was p lambda, right, nm, right, and the other was q lambda nm, correct? Yeah, so if you find that this is non-empty and this is empty, correct? Yes, say you find for every n and m, and when m is whatever 2 to the polylog n, so for all n going to infinity and when m is equal to something, you find such lambda, say you have proven this, right? You show that there exists a lambda such that this polytope is non-empty and this is empty, yes? Then all you have to do is, you have to just take k times lambda, so that when you stretch it appropriately, that k times lambda, this polytope would contain an integer point and this would still be empty. So that then is an obstruction. That's all. So that is all you need to know.
Yeah, but it's not clear when you say, so I just don't understand. So how to prove pH? pH was a statement about particular groups.
How to prove
before, but when you go to the leak, you have to
prove pH for the similar
yeah,
functions?
for the lift, where basically the group action is more complicated.
Yes, yes.
Yeah.
But the similar kind of result is proven there, assuming that the singularities of class varieties are rational, that the stretching function is again quasi-polynomial. So if you want to disprove the program, you will have to prove that. Yeah.
Find some other.
No, no, that.
Quasi-periodicity
Yes.
you took care of.
Yes. No, but
You were going to indicate one very important thing, and that is this naturality that some people were worried about in the first lecture changed. There was some phase.
No, we were not worried about it because we clarified it from the beginning. He's attacking, he's proving a low bound for particular functions, but this polynomial is permanent, right? And this low bound attack would not prove a low bound for another polynomial, for even a single more polynomial, because he's using the symmetries of this particular one.
correct.
Most low bound, most low bounds that were proved for weak classes of computations, when they prove a low bound for something, they automatically, the same method, the same proof method, generates a low bound for almost every function.
Okay, but there was a discussion about how big. You're trying to show you can't write permanent in terms of determinant in terms of certain sizes, and if you let that get.
That's another question.
Yeah, I
this
see
was
how
nothing
that
to do with the.
Yeah.
How does that enter into
Yeah, yeah. So that.
Just say that is
Yes. Yeah. So let.
That's my question.
Oh, that is your question. Because in the weak case, what happened was that this polytope had too few constraints, and it always remained empty when you made m as large. Okay. When you get it actually for the thing, after a while this polytope actually would become empty, because it would kind of shrink. That shrinking is not happening now because there are too few constraints and actually just remaining non-empty all the time. That is why it.
So where do I see this phase transition? Have you made some computation which shows that this changes at
No. So there are some results. So all the results say that if the permanent versus determinant is actually true, then it gives good mathematical evidence to believe that actually these such obstructions would actually exist. Okay, so not.
But there is a reason. Is there a reason to believe that this will happen? This
Yes.
At quasi-polynomial.
Yes.
N to the n to the log
As-
n.
Into the not as long as the permanent is not expressible by determinant.
I see. So that's just a number you wrote down. You say the true lower bound should follow from.
But you didn't come up with that through some thought.
Hmm?
You didn't come up with that number through this analysis by saying something changes representation.
Not.
theoretically.
Yeah. Not. That would come about only when those polytopes are there. Right now I can't say anything. Yeah. If that is what you want.
Can you say what machinery is there? So what kind of machinery? You mentioned the Riemann hypothesis. What kind of machinery is there to prove such positivity?
Yeah. So the point is that in the case of Littlewood-Richardson coefficient, one natural proof of positivity comes through the standard quantum groups. Yeah. So what in GCT 7-8 is done is that quantum group is lifted to the placism problem, and one has to do the lift that. So the Littlewood-Richardson is the basic prototype. So you have to basically lift those properties to this new quantum group, and then if those things, the conjecture is that if those quantum group have the similar properties as the standard quantum groups, for which there is good evidence, then yes, those positivity things would come about. Yeah. So that is how actually the whole plan of attack is, and there the properties of the non-standard the standard quantum group are intimately linked with the Riemann hypothesis of finite fields, and so that is what has to be, that machinery is what would need to be extended to get these kinds of pH in this way. Yeah. So of course, as we said, what we have done so far is just the easy part. The hard part is this. Okay. So but it is our hope that the field will give a thought to the easy part and have something to say.
Find it easier, so.